Welcome to my science tutorial. In this video we are going to be looking at empirical formula and quantitative analysis. Alright, so let's get started. Right, there are three ways by which organic compounds are written in terms of their formula. We have the empirical formula, we have structural formula, and we also have the molecular formula. Alright, so what is the differences between them? Alright, when you have empirical formula, as it states here, it shows the simplest whole number ratio of atoms in a compound. The structural formula shows how atoms or elements in a compound are bonded to each other. And then we have the molecular formula, which shows the actual whole number ratio of elements or atom in a compound. So in this video we're going to focus on empirical formula. So we're going to look at how formulas are written and how they can be converted to empirical formula. So let's look at some example. We're going to write MF for our molecular formula, EF for empirical formula, and SF for our structural formula. So what we have right here is 2 carbon atoms and 6 hydrogen atoms. It is in a whole number ratio of 2 is to 6. So we can say this is our molecular formula of ethane. Okay, if we want to leave this any simplest whole number ratio, then we know our 2 can go into the 6 3 times. So the ratio now is going to be what 2 is to 3. So when we rewrite this, it's going to be a CH3. So we know that we have 1 carbon and 3 hydrogens, which is the simplest whole number ratio if we take this compound. Alright, so we are going to label this as our empirical formula. Okay, what if we decide to show all the connections which we have inside this compound here? If we do that, then we're going to have our 2 carbons and we'll show our connections of all the hydrogens inside there. We are going to call this our structural formula. Now the structural formula comes in 2 forms. For this one, which we can see all the connectivity of the hydrogens to the carbons, we'll say that this structural formula is an open structure. What if we decide to write it in the condensed form as CH3? We still have our 2 carbons there and our 6 hydrogen. When we do this, then it's simply called the condensed structure, and there are all types of what structural formula. Okay, now quantitative analysis is carried out to determine how much of a molecule, element, or atom there is in a compound. So it is that part of organic chemistry where we try to measure the specific amount of an atom that is composed in a compound. So when we define a quantitative analysis, we can do away with this question: how much? Okay, so in many experiments in organic chemistry, for example, in combustion, we determine the percentage of carbon dioxide that has been given out, or water that has been produced, or the amount of a molecule that has been produced. We can further go ahead to find out how much of carbon we have inside there or oxygen we have inside there. In trying to do all this, then we are trying to quantify specific elements or atoms that we have in the compound. When quantitative analysis is carried out, it is easier to determine the amount of or to find the atomic composition of a compound in percentage, and once we are able to find all the percentages they compose in a compound, then it will be easier to determine the empirical formula of the compound you are dealing with. So we'll go ahead and look at equation, and we'll see how we can combine quantitative analysis and empirical formula. So the question right here says 0.8 grams of an organic compound on combustion in pure oxygen gives 2.63 grams of carbon dioxide and 1.28 grams of H2O. We are being asked to calculate the empirical formula of the compound, which means we should leave our formula in the simplest whole number ratio. So how do you think we should do? Alright, let's go ahead and summarize the information we have in the question. So we have our mass. We have our mass of organic compound. We'll just write OC, which is equal to 0.86 grams. 86 grams, and then we have mass of carbon dioxide, which is produced to be 2.63 grams. We have water, mass of water to be 1.28 grams. So we are going to use these parameters and derive the empirical formula of the compound. Now we are going to find the percentage of carbon and the percentage of hydrogen we have in the compound. So let's go ahead. We know that the molar mass of carbon is 12, that of hydrogen is 1. So from the information we have right here, we are going to see how we can use this to get the mass of carbon. So starting with the carbon dioxide, we know that 1 mole of carbon dioxide will contain 44 grams of the carbon dioxide, carbon and oxygen inside there. So that's why there will be the molar mass. That will be the molar mass. And if 1 mole contains 44 grams, then we're going to find how much of this carbon dioxide, how much of carbon we have in the carbon dioxide. So we'll go ahead and do that. Now you might be wondering how we got the 44 grams. Oxygen has a molar mass of 16. So if we calculate that, we have our carbon dioxide. So carbon is 12, oxygen is 16, and then we have 2 moles of the oxygen. So when we calculate that, we're going to have 44 grams per mole of the carbon dioxide. Okay, so that is how we have our 44 grams by mass in 1 mole of the carbon dioxide. Okay, so we know that in this 44 we have carbon constituting 12 grams. Okay, so if in 44 grams we have carbon constituting 12, what about in 2.63 grams, or to be the mass of carbon. So let's go ahead and cross multiply, and if we do that, the mass of carbon will be equal to 12 times 2.63 divided by the molar mass, which is at 44. So when we do that and punch that on the calculator, we are going to get, let me punch that, we are going to get carbon to be 0.717 grams. Okay, now let's find the percentage of carbon in the compound. So we are going to divide the mass of carbon by the mass of the compound and multiply by 100. So percentage of carbon will be equal to 0.717 divided by the mass of the compound, which is 0.86 times 100. So if we punch that, we're going to have 83.40%. Okay, so now let's go ahead and find the percentage of hydrogen in the compound. Okay, let's go ahead and have a look at how much of the hydrogen we have. So let's go ahead and calculate the molar mass of water. Molar mass of water. There is water is 2O, hydrogen is 1, so we have 2 times 1 plus oxygen, which is 16. So that is giving us 18 grams per mole. 18 grams per mole as the molar mass of water. Alright, so what this means is that in every 1 mole of water, total mass of hydrogen and oxygen will be 18 grams. 18 grams. Now in this 18 grams, hydrogen is contributing 2 grams. 2 grams. Okay, if hydrogen is contributing 2 grams, let's go ahead and find how much of the mass of hydrogen will be in the organic compound. In 18 grams, hydrogen is contributing 2. Then in 1.28 grams, let's call it M. So let's go ahead and cross multiply. Our M, which is mass of hydrogen, will now be 2 times 1.28 divided by 18 grams. So let's go ahead and punch that. When we punch that, we'll get 0.142 grams of hydrogen. Okay, now look at the percentage of hydrogen in the organic compound. So this will be 0.142 grams divided by 0.86 times 100. If we go ahead and punch that, we will have 16.33%. Sorry, 53%. So by the end of the quantitative analysis, it has been found that carbon contains 83.40% and hydrogen 16.53%. Let's go ahead and add that and see what we get. So 83.40 plus 16.53, when we punch that, then we're going to have 99.93%, which is approximately 100%. So this is giving us a fair idea that our unknown organic compound is purely hydrocarbon. Find the empirical formula. In doing this, we'll first find the atomic moles. Atomic mole, and then we'll find the relative mole. Okay, so let's go ahead and do that. So let's write our carbon and our hydrogen. Our carbon and our hydrogen. How do we find the atomic mole? We'll simply divide their percentages, the percentage abundance, by their molar mass. So for carbon, it is going to be 83.40 divided by 12, and for hydrogen 16.53 divided by 1. So when we do this, then we can see it is our atomic mole. For carbon, it will be equal to 6.95, and hydrogen will give us 16.53. Okay, so next we'll find the relative moles. How do we do that? We'll take the relative moles. That of carbon is 6.95, and that of hydrogen is 16.53, and then we'll divide through by the smallest among the relative moles. So in this case, our 6.95 is the smallest among the relative moles, so we are going to divide through with that, and if we do that, then it will be 6.95 over here 6.95. For carbon, it's going to give us 1, and for hydrogen, it's going to give us 2.38. Okay, so this is giving us a fair idea of how this is going. We said empirical formula deals with the simplest whole number ratio, and if we look at this right here, it is in decimal, so we have to find a number which we can use to multiply so that we can get a whole number. So let's multiply through by 3 and see what we'll get. So when we multiply by 3 our carbon times 3 will give us what? 3. And if we take that of hydrogen, we multiply through by 3, then we should be getting 7.14, and then we can see approximately it is 7. So how do we write our empirical formula? We know the number of carbons, and we know the number of hydrogens. So quickly we just write a carbon and a hydrogen 7, and this right here is our empirical formula. Okay, in other questions concerning empirical formula where you are given percentages of the elements and you add them up and it's not up to 100, then the difference after you subtract it from 100 will correspond to the oxygen. So you just go ahead and find the atomic moles and then the relative moles, and then you get your empirical formula. This is the end of the video. If you like this video, click the like button and hit the subscribe button to get notified when new videos have been uploaded. Thank you.